Today, we have a fantastic number theory problem that looks simple on the surface, but forces us to use two completely different mathematical toolkits to solve. Here's the challenge. We need to find all pairs of prime numbers PQ such that two specific conditions are met. P minus Q is a perfect square. PQ minus Q is also a perfect square. Now, whenever we see primes and squares mixing together, we should immediately think of two things: modular arithmetic, to find the restrictions, and magnitude bounds, to see if numbers get too big too fast. So we are going to need both. Let's dive in. Part 1. We can say the small case. So, the small case is, you can call this as case 1. Q equals to 2. First, let's deal with the parity of primes. Primes are usually odd with one very famous exception, the number 2. It's always a good strategy to check Q equals to 2 separately because it behaves differently. Let's plug Q equals to 2 into our expressions. We'll have P minus 2 equals to A squared. And 2P minus 2 is equal to B squared. So we have 2 times P minus 1 equals to B squared. Look at that second equation. 2 times P minus 1 equals to B squared. This tells us that 2 times P minus 1 is a perfect square. For 2 times something to be a perfect square, that something must also have a factor of 2 to complete the pair. This implies that P minus 1 is even, so P is odd. That's expected. But let's look closer. We have P minus 2 is a square, and 2 times P minus 1 is also a square. Well, we can look at these modulo 3. Why 3? Because squares modulo 3 are quite restrictive. If we have a perfect square, then we know that if we call this as x squared, it must be congruent to 0 or 1. Mod 3. You can never have a square congruent to 2 modulo 3. Now let's test our prime P modulo 3. And we'll find out that if P is congruent to 1 mod 3, P minus 2 is congruent to negative 1 mod 2 mod 3. But 2 is not a square, so P cannot be 1 mod 3. This will mean that P must be congruent to 2 mod 3. So then we can find out that P must be divisible by 3. Since P is prime, P must be equal to 3. For this case, PQ is going to be 3, 2. And now the more general case, where Q is greater than 2. Now for the interesting part, what if Q is an odd prime? Let's write our two squares as A squared and B squared. So then we'll have P minus Q equals to A squared. And then PQ minus Q minus Q equals to B squared. Let's factor that second equation. So then we have Q times P minus 1 equals to B squared. Since Q is a prime number and divides in square B squared, Q must appear in the prime factorization of B squared with an even exponent. Since there is already one Q on the left, P minus 1 must contain another factor of Q and potentially some other square. So we can write P minus 1 is equal to Q times K squared for some integer K. This gives us a formula for P. P is going to be equal to QK squared plus 1. Now we have two paths based on what K is. Path A is, what if K is equal to 1? Well, if we have K equal to 1, then P equals to Q times 1 squared plus 1 equals to Q plus 1. We are looking for two primes that are exactly 1 apart. Since Q is greater than 2, Q is odd, which means that P will be even. the only even prime is 2, but we already said that q is greater than 2, so p must be greater than 3, which is impossible. So if q equals to 2, we already got as our previous answer that p is equal to 3. But for odd q, there will be no solutions. So pat B. What if k is greater than or equal to 2? Well, k is greater than or equal to 2. P equals to qk squared plus 1. This is greater than or equal to 4q plus 1. We got the 4 from 2 squared, which is 4. This implies p is much larger than q. Specifically, p is greater than 4q. So keep this inequality in your pocket, p greater than 4q. We're going to use it to break the problem. And now, we have two square equations. So the reflex is to subtract them to see what happens through difference of squares. We can say that b squared minus a squared equals to pq minus q minus p minus q. So b squared minus a squared equals to pq minus p. So we can factor both sides. We'll have b minus a times b plus a by difference of squares equals to p times q minus 1. Now factor the left side through difference of squares. So that's how we got to this equation here. Now the crucial step, p is a prime number. If a prime divides a product, it must divide one of the factors. So p must divide b minus a or p must divide b plus a. Now let's check the sides of these numbers. Recall that b squared equals to pq minus q. So we know that b squared equals to pq minus q. This is less than pq, obviously. So b is less than square root of bq. Also, a squared equals to p minus q, which is less than p. So a less than square root of p. Let's look at the difference, b minus a. Since b is less than square root pq, and we are in a case where q is less than p, where actually 4q is less than p, b is roughly p times smallest, the entire thing square root. Strictly speaking, since q is less than p, b is less than p. Actually, even stronger, since b squared is equal to p times q minus 1. Less than p squared. We know that b is less than p. And since a is greater than 0, we have b minus a is less than b is less than p. Wait, catch that? B minus a is strictly smaller than p. So p cannot divide b minus a because the number cannot divide a smaller positive number. So we can get a conclusion from this, which is that from this we get p must divide b plus a. So we'll have b plus a greater than or equal to p. Now the contradiction. We have established that b plus a greater than or equal to p, so we can divide everything by square root p to make it easier to see. So then we'll get b equals to square root pq minus q, a equals to square root p minus q. So then we can combine this. So we'll have square root of pq minus q divided by square root of p. plus square root of p minus q divided by square root of p. This is greater than or equal to square root of p. Look at the first term. Square root of pq minus q divided by square root of p equals to square root of q minus q over p. This is strictly less than square root q. So we can say that this term is less than square root q. And the second term, square root p minus q divided by square root p is equal to 1 minus q over p square root. This is strictly less than 1. So then we'll have, if you add them up, there's something less than square root q plus something less than 1. This is greater than the left side, greater than or equal to square root p. So we can get the inequality that square root q plus 1 is greater than square root of p. Now remember path B, we assume that k is greater than or equal to 2, which forces p greater than 4q. This means that square root p greater than square root 4q equals to 2 square root q. So we can combine them to get that 2 square root q less than square root p less than square root q plus 1, and 2 square root q less than square root q plus 1. Subtract square root q from both sides, so we'll have, so then we'll get that square root q is less than 1. And this is impossible because it will imply that q is less than 1, however p is a prime number. So the conclusion is that the assumption that k is greater than or equal to 2 leads to a contradiction. The assumption that k equals to 1 leads to no solutions for all primes. Therefore, there are no solutions for q greater than 2. So, since this is impossible, we'll get that this will lead us to no solution for case 2. So the only answer to this problem would then be, the only parallel prime is going to be 3, 2. So the answer to this problem would be, the only pairs of primes pq, for which p minus q and pq minus q are both square, is 3, 2. So that's how you solve this problem, and thanks for watching.